Okay. So we're going to start talking now about the atom and kind of the composition of the atom. How did we discover the atom? What is the atom made of? And really get a grasp on this idea of the atom and what it is, okay? Because that's the basis of chemistry. Everything, all these chemical reactions, they happen at the atomic level. So we need to understand how they're happening and what is the atom made of that allows this stuff to happen. So the atom is the basic structural unit of an element. So we see all the elements here. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Okay? So we have lots of different elements. Okay? And they are composed of atoms as their very basic unit. Okay? There are three primary particles within an atom, and those are protons, neutrons, and electrons. So all atoms are made up of these things, these protons, and these neutrons, and these electrons. The nucleus of an atom is a small, dense, positively charged region in the center of the atom. That contains the protons and the neutrons. So that's the nucleus. That's why it's positively charged, because protons are positively charged particles. Neutrons have no charge. So the only charges there are from the protons, and therefore the nucleus is positively charged. It's dense, it's small, and it's tightly packed. And then surrounding that would be the electrons. So the electrons are negatively charged particles. They're located on the outside of the nucleus of the atom. So they're surrounding that nucleus. They're moving rapidly, okay, in what we would consider a relatively large volume for an electron. So if you consider how small an atom is small, right? But then if you consider how small an electron is even way smaller than that. So the space in which it moves is a large volume to it because it's such a tiny thing. Okay? And the size of an atom is basically due to the volume that electron moves in. So if the electrons are attracted more strongly to the nucleus, they move in a smaller volume, and the atom would be smaller. But if they don't have as strong of an attraction to that nucleus, then they would be moving in a larger volume because the attraction isn't as strong, so they're not as closely drawn to the nucleus, and so they're moving in a larger volume, and therefore the atom is larger. So the atom has this very tiny central region and these electrons that are just moving around it in these large volumes. Okay? The atom is mostly empty space. That's what it is. You're probably looking at your table like, well, how can that be if this is made up of atoms and it's mostly empty space? Okay? So matter, atoms, bound together, create these surfaces, but there is lots of empty space between all the atoms and molecules. Okay? That's why I can have a wireless device in another room and I can receive signals from it, right? Because those electromagnetic radiation can travel through the empty spaces of the atoms through the solid matter, right? And it can be brought to us in this room, okay? So protons and electrons have charges that are equal in magnitude but opposite in sign. So if I have one proton and I have one electron, protons are positively charged, electrons are negatively charged, they would attract to one another. Because the strength of the attraction is exactly the same between them. That's what it means by the magnitude of the charge is the same, but it's just opposite. Okay, so the strength of the attraction is exactly the same. That was was weird. Whoa. My note, where'd you go? It's cleaning up. Okay. Let's get on. All right. Interesting. Okay. So a neutral atom is an atom that has the exact same number of protons as it does electrons. Because if it has the same number of protons as it does electrons, they balance each other. And you are left with a zero charge. And that's what we would consider most of the elements to be at a zero charge. Now, if you change the number of electrons, you will change the charge that is on that atom. Think about if I lose electrons. Let's say I had 10 protons and I had 10 electrons. Protons are positively charged, electrons are negatively charged. This is balanced, right? So the net charge here is 0. Well, what if I went from 10 electrons to 11 electrons? Now what's the charge? Negative. What if I went to 12 electrons? What's the charge now? Negative 2, right? I have 2 more negative charges than I have protons. So that means it's unbalanced now. Now the atom is negatively charged. Okay? What would be the charge of this element? Positive 2. Okay? Well, how do I get there? Well, I don't actually add protons. Protons are consistent. They don't change. If I change the number of protons, I change the element. The element is determined by the number of protons. So, element 14 is silicon. It has 14 protons. That is constant. So if I didn't change the number of protons in this element, what did I change? Good, I changed the electrons. What happened to the number of electrons? Or what happened? How many electrons did I start out with?
10.
Before I had 12, silicon would have started out with how many electrons? 14. It would have, because it would have started out with a 0 charge. How did it get to 12? It would have to have lost 2 electrons. So it is the electrons that are gained or lost, not the protons. The protons are in the nucleus. They're constant. If I change the number of protons through nuclear chemistry, I would change the element. I would no longer be silicon if I change it from 14 protons to 13 protons. I change its identity if I do that. Okay? So if I am silicon, I will always have 14 protons. That's constant. That doesn't change. The number of electrons can change, and if I lose or gain electrons, it will change the charge on the element. Okay? To either positive or negative. So if I have an oxygen that has 8 right there. Has 8 protons. And let's say it has 8 electrons. And it gains 2 more electrons. Now it has 10. What's its charge? Negative 2. O2 minus would be its charge. Okay? Has a negative 2 charge. So, if you're dyslexic, this is great. Because plus is minus, minus is plus. Okay? It makes sense to me. Okay? So, if you add electrons, you gain negative charges. If you lose electrons, you lose negative charges. You become more positively charged because the protons are outnumbering the electrons. Okay? So minus 2 electrons, now I have a plus 2 charge. Plus 2 electrons, now I have a negative 2 charge. Okay? So it's exactly backwards. Okay? So you'll find that to be true in chemistry a lot. It happens a lot. So I'm serious. If you're dyslexic, this is great. This is a great class for you. Okay? But if you're not, you're going to have to work that out in your head. Okay? Okay, so this is how we represent everything. The atomic number is Z. The atomic number is what we find here. So oxygen has an atomic number of 8. So when I wrote it, I wrote the atomic number right here for oxygen as 8. This is the mass. And it's the mass in a whole number. We're not talking about this mass. This is the mass of oxygen, 15.9994. But that's not the one we would write here on the atomic symbol. Okay? We would write the mass of this atom, which is either 15 or 16 or 17, something like that. It's a whole number. Okay? So I could have oxygen 16 or oxygen 15. Okay? And they would all have the same number of protons. The number of protons does not change. But you can see the mass can change. So if the mass can change, but the protons can't change, and let me say this, and electrons don't contribute to the mass of an element because they're too light, then what's causing that change in the mass? Are there only electrons and protons in an element? What else? Neutrons. Okay. Well, guess what? The number of neutrons can change in the nucleus of an atom. And if I change the number of neutrons, I will change the mass of that element. The number of protons determines the element, what it is. The number of neutrons will determine the mass. So if I have 8 protons, and protons and neutrons have the same mass, and my mass is 16, how many neutrons do you think I have? 8. If I have a mass of 16, that means I have 8 neutrons and 8 protons. Well, what if I'm oxygen 15? How many neutrons do I have? I have 7 neutrons and 8 protons. Okay? So you can almost see why they set it up in this fashion. Because it's easy to subtract 8 from 16, find the number of neutrons. 8 from 15, find the number of neutrons. I have 8 neutrons here, I have 7 neutrons here. Okay? The mass of an element is determined by the number of protons and the neutrons. You guys just figured that out. The sum of the number of protons and neutrons is its mass. Okay? That's its mass. Okay, here's a bunch of confusing stuff. Okay, mass number, number of protons plus number of neutrons. Okay, that's what we just said. Number of neutrons, mass minus the protons. Number of neutrons, mass minus the atomic number, which is exactly what this is saying. That the number of protons is the atomic number. Okay, so a lot of times you could potentially not even be given the atomic number, and they'll ask you the number of neutrons. All you have to do is look here. Okay? How many neutrons are in P32? This is phosphorus, 32. So I look good. So I look over here and I say, oh, 15 here. 15 protons. 17. So 17 neutrons. Okay? I have 17 neutrons. So they didn't tell me that the mass or the atomic number was 15, but I just had to look there to find it. It's on the periodic table. Okay? Okay. All right, this is just kind of showing the actual masses in gram quantities. So what we were just calculating the mass of an atom to be was to be in atomic mass units. For a single atom, 1 proton weighs 1 atomic mass unit, 1 neutron weighs 1 atomic mass unit. But if you consider the gram amounts of everything, okay, a proton weighs 1.6726 times 10 negative 24. Neutrons weigh 1.6750 times 10 negative 24. So we essentially say they're about the same. Each has a mass of 1 atomic mass unit. This is insignificant compared to these. Okay, the masses of these are so much heavier that this we don't really consider it to contribute to the mass of the entire element. Okay, so what does that number represent? It's in scientific notation. Okay, scientific notation. If I write it out here, it would be 0.1. Okay, that's what that number is. That's the mass of a single proton. Okay, so you can see we work with stuff that is pretty small when we're talking about atoms. We deal with very small things. Okay, and we're going to show you how we're going to take it from a very small thing to something that we can actually conceive of and perceive. Okay? And we're going to do that by just basically, instead of working with single atoms, which we can't do, we're going to work with a lot of atoms. So in the laboratory, I don't weigh out single atoms on my scale, right? I don't carry out chemical reactions with a single atom. I carry out chemical reactions with 5 grams of a substance or 10 grams of a substance. Okay? And how does that relate to the number of atoms? Well, I can figure out how many atoms are in that mass that I have in the laboratory. And then I know how many atoms I need of this and how many atoms I need of this and react them to form my compound. Okay? So we deal with very small things. So we have to use very large amounts of them. That's the idea behind this. Okay? Okay, calculate the number of protons, neutrons, and electrons in each of these. So boron 11 has how many, what are we starting with? Protons, neutrons, electrons. How many protons? 5. Neutrons, electrons. Is there a charge on it? What does that mean? It has the same number of protons as it does electrons. They're balanced. So how many electrons do I have? 5. Protons, neutrons, electrons. How about of iron? 55. Number of protons? 26. Neutrons. Say it again. 31. Electrons. 26. Okay. Okay, so that's how I do it. Okay? That's some of the simplest math you're going to do in here. I'll tell you right now. Okay? We'll start you out easy because it's going to get a little more complicated. Okay, so hydrogen. These are 3 different atoms of hydrogen. Each one has a different mass. You have hydrogen that has no neutrons, has a mass of 1. You have hydrogen that has 1 neutron that has a mass of 2. And you have hydrogen with 2 neutrons that has a mass of 3. So we call this deuterium and this tritium. Okay? And H2O, that's water. D2O is called heavy water because it's heavy. The hydrogens of deuterium are heavier than the hydrogen itself without any neutrons. And we would say that's D2O, heavy water, which is radioactive. Okay? Well, how is something radioactive? Something that's radioactive is something that has a nucleus that decays. This is not radioactive. This is. It will decay. So if your nucleus decays, it's considered to be radioactive. Okay? These are radioactive isotopes of hydrogen. Okay? Both of these are. Both of these would decay after a certain amount of time. And they will release energy and things of that nature as they do so. Okay? So almost all elements have isotopes of themselves. Carbon. Carbon has isotopes. Carbon-13, carbon-14. Those are radioactive isotopes of carbon. They are not as stable as carbon-12. Carbon-12 is the isotope of carbon that is not radioactive. And it is the isotope of carbon that constitutes most of the carbon, which makes sense because it is not radioactive and all the other carbons are radioactive, so that means they decay and become something different than carbon over time. Okay? Now, albeit it takes a long time for carbon-13 to decay, like thousands of years, so it sticks around for a long time, but it does decay and release radioactivity. So if you have a sample of carbon-13, it's radioactive because decay is occurring within that sample. Okay? But these are what we call isotopes. Isotopes are the same element, but different masses. They have a different mass because of the number of neutrons that are associated with the isotope, which makes the nucleus unstable. So by adding those neutrons, the nucleus becomes unstable and can decay and become radioactive. Okay, so now if we look at chlorine, the atomic number of chlorine is 17. Okay? That means it has 17 protons, right? So here's chlorine. 17 protons. Now look at its mass. 35.453. Okay, but what I just told you is that if you're an element, you have to have an exact mass. It needs to be a mass of either 35 or 34 or 36, right? It needs to be something like that, not 35.453. So where does this number come from? Okay, so this is not the mass of an isotope of chlorine. It is the mass, it is the average mass of all chlorine atoms. So if you take a sample of chlorine, so I go in the laboratory and measure out chlorine. In that chlorine sample, there will be mostly chlorine-35, the stable isotope, but then also there will be trace amounts of the other isotopes of chlorine. Yes, the radioactive isotopes, but they're very trace amounts, so we don't really in fact, you have, let's talk about carbon. Carbon-12, carbon-13, carbon-14, okay? We have lots of carbon in us. We're made up of organic material that's built from carbon, okay? And within us, there is an exact amount of carbon. Well, I shouldn't say exact amount, but there's a percentage of carbon-12, carbon-13, and carbon-14. So yes, you guys are radioactive. Okay? So, but that's how carbon dating works. Have you heard of that, carbon dating? Where they take a fossil that's an organic, of organic origin, and they can calculate how old it is because they know that if you have this amount of carbon, you should have, of that sample of carbon, you should have a certain percentage of it be carbon-13. And they will calculate how much carbon-13 is actually in that sample, that fossil, and compare it to how much should be there. And based off the difference, they understand how old it is because of how much it's decayed. How much has that carbon-13 decayed over a period of time, okay, over those thousands of years. And they can determine a date. That's carbon dating. Okay, that's how it works. Because all of us, every sample of an element has the isotopes of itself within that sample. Okay? Now you can enrich isotopes. That's where it gets more dangerous. So I can enrich P32, which is radioactive. I can enrich that isotope, and then I have a sample of that isotope, and that's very dangerous. That's more dangerous, right? But just having a sample of phosphorus, it's not dangerous, because we deal with radioactivity all the time in our life. The sun, ourselves, our phones, everything around us, right? But we don't, we're not affected by it because our bodies can handle that. But if we enrich a sample of an isotope, that's when it becomes dangerous. That's when it's bad. So if I weigh out a chemical in the laboratory, I weigh it to those masses because it contains not only sulfur 32, but it contains sulfur 33 and etc. And so I have to weigh it out to 32.06 to understand exactly how many atoms I have of that sulfur in that sample. Okay, so that's what we're considering here with these. So this number, 35.34, it's a weighted average of all the isotopes. Okay, chlorine consists of chlorine 35 and 37 in a 3-to-1 ratio. Okay, so we would find the weighted average of those, and it would give us that mass on the periodic table. So here we go. Here's an example. Calculate the atomic mass of naturally occurring chlorine if 75.77% of chlorine atoms are 35 and 24.23% are 37. Okay, now the way, this is going to go through steps, and that's great, but what I would recommend is that you make a chart, okay? The mass, the abundance, okay? And here we have chlorine 35 and chlorine 37. And those are their masses, 35 grams and 37 grams. And then, or atomic mass units, I guess at this point, we'll say atomic mass units. And then multiply them by their percent abundance. Chlorine 35 is 75.77% abundant. Chlorine 37 is 24.23%. Now, if you multiply something by its percentage, what do you have to do to it first? Can I just say 35 times 75.77? What do I have to do? You have to turn it into its fraction, its decimal. Okay? So I have to divide it by 100 to get it back to its decimal. Divide it by 100, and that's going to move this decimal place 2 places. Okay? So it's going to be 0.7577. Okay? So 35 times 0.7577. That would be me multiplying 35 by 75%. And here, I'm going to move the decimal to be 0.2423. 37 times 24.23%. Okay? Okay? So what is that? Go ahead and do that for me. What is 35 times 0.7577? Say it again. Okay. How about the next one? 8.97. Okay, now all that's left to do is to add those two numbers together. 26.52 plus 8.97, what do you get? 35 point what? 49. Oh, that's fine.
Okay.
So, or we'll just say 35.5. Okay. Okay. Is that where we were supposed to get? Yeah, we're supposed to get about 35.5. That's where we're trying to get. Okay. So this needs to match what you see up there. If you do one of these calculations and it's not matching, you know, relatively close, it doesn't have to be exactly the same, but that's pretty close. If I'm not getting that, I did something wrong. Okay? That's where I should be getting to. Okay? All right, so let's see what they came out with. They came out the same, right? 35.5. So they took the percent divided by the mass, percent times the mass, and then they added those together, and they found 35.5. I like to put it in that chart because it just makes it flow real easy of what I'm supposed to do. This times that, and then add them together. Okay?
So these will be some problems on the homework that we will have to figure out?
Yes.
Okay. All right.
Yeah, you'll have to do these types of problems.
Do you want us to round or leave it?
You can round. Okay? When you're doing the calculation, it's always best that, like from here to here, see how they just did 26.5 and 38.97? It would be better to carry all that out because you're going to put it here and add them together, and then your final answer around that. But it's always best that in the middle of the calculation to just carry everything instead of rounding in the middle, because then that affects your final answer, albeit sometimes just by an insignificant amount, but sometimes it's not an insignificant amount, and then your answer is a little farther off and you're worried about that. So I would say when you're doing these calculations, round your final answer, but carry all your numbers out, okay, as far as is reasonable. Okay. So if you have one of the calculators where you can just type it in as one single equation, that's great because it'll just calculate your final answer and carry everything out. But if not, then carry as many decimal places as you can each step. Okay? And then when you find your final answer, round that. All right? Okay. Here we go. Neon has 3 naturally occurring isotopes. What is the atomic mass of neon? Do that one. Look how nice they were. They set up the mass, the abundance, everything for you already. Okay, so what did you guys find for 20 times 0.9048? 18.096. Okay. 21 times 0.0027.
0.0567.
Like that?
Yes.
Okay. And 22 times 0.0925.
2.035.
Okay, and then you added those together and you found what?
7.18.
Okay, so neon has an atomic mass of 20.18. Good, right? So that's basically what that periodic table is telling me. It's matching. So it's working. It's working. Okay, so now let's talk about how we got this idea of the atom. Where did it come from? And Dalton, he was one of the first scientists who actually did experimentally based theories of the atom. He did experimentation for the basis of his theories that he developed. Okay, and he developed some very interesting theories about the atom that actually hold very close to true even today. Okay, and this was a long time ago. So Dalton, he theorized that all matter, which we defined matter the other day, so anything that has mass occupies space, so everything around us, okay, all this matter consists of tiny particles called atoms. He also theorized that an atom cannot be created, divided, destroyed, or converted to any other type of atom. So he's saying, if I am an atom of oxygen, that's who I am. And when I undergo a chemical reaction, I maintain my identity as an oxygen atom. Right? So H2 plus O2 produces H2O. It's an oxygen atom here. It's an oxygen atom here. It maintained its identity as an oxygen. It's just now become a compound. It's now bound to hydrogen. Okay? But it is still an oxygen atom within that compound. So that's what he's trying to say. And I could decompose this H2O decomposed into H2 plus O2. Oxygen is still maintaining its identity. I'm not destroying the oxygen. I'm not creating the oxygen. I'm just moving it around. That's all I'm doing. Okay? So that's how he understood it, and that works. For chemical reactions, that works. Where it doesn't work, and where he didn't understand it doesn't work, is on the nucleus level. So I can change my my radioactive isotopes, like of your let's see, where's it? Well, even if it was just a radioactive isotope of phosphorus, it could decay into a lower element of silicon. Okay? So it can change if you change it at that nucleus level, but he didn't understand that. So looking at this, how it works in a chemical reaction, it's spot on what he's saying. Okay? These elements will go from one to will just simply be moved around. I didn't create the oxygen. I didn't destroy it. It's just getting moved around. Okay, 3. Atoms of a particular element have identical properties. So he's saying, okay, if I have one atom of oxygen, it reacts with hydrogen. And that's true. Oxygen reacts with hydrogen no matter what isotope it is of oxygen. But what he didn't know about was isotopes. He didn't know that you have an O15 and an O16, or a nitrogen 14 and a nitrogen 13. He didn't understand that. So that would create a few different properties of mass, but not chemical properties. The chemical properties are the same. Okay? They react the same. They just have different masses. So that's another one that we would maybe fix a little, but he's got a very good grasp on the idea behind it. Okay? Atoms of different elements have different properties. Yes, if you're an oxygen, you're different than a sulfur. You're different than a nitrogen. Okay? They have different properties. They react differently. Atoms of different elements combine in simple whole number ratios to produce compounds. Yes. H2 plus O2 produces H2O, not H1.5O, right? They're whole number combinations of these elements. That's how they come together. Okay? As entire atoms. On the atomic level, that's how they're interacting. As individual atoms. And that's how they combine. Okay? Chemical change involves joining, separating, or rearranging the atoms. Yes. So that's what we're showing in those chemical reactions as well. So most of his postulates are still okay. You can see 2 and 3 are kind of left out there. 1, 4, 5, and 6 are still regarded as true even today. Okay? And those other 2 were so close. If you're not looking at the nuclear level, he's right on. Okay? And his experimental basis of that was telling him that that's true. So if I didn't understand the atomic level either, those are the conclusions I would come to. That's how these atoms are working. Okay, so now after Dalton, he comes up with his theories. Now we have another scientist, J.J. Thomson. And J.J. Thomson wants to understand, well, so we have these atoms, they react in these ways, the molecules move around. But what are those atoms made of? What do they consist of? He wants to understand the particles of the atom. Okay? And so he developed this this ray tube where he can take these electrical atomic particles and he can shoot them through by creating a ray. Here you have the cathode, the anode. So he's creating this ray from the cathode to the anode from a battery, high voltage, well, not a battery, but a high voltage charge across this. And it's pulling those particles, whatever they are, he doesn't know what they are, through that ray tube, okay, as a beam. And you can actually see that beam, okay, in this ray tube. So he shoots those atomic particles through here. And then he has these 2 plates and a magnet. Okay, here's a positive plate. Here's a negative plate. When he turns on the positive plate, so with it off, they would just shoot right through. Okay? If he turns on the positive plate, it gets deflected this way. If he turns on the negative plate, it gets deflected this way. So, what do you think that particle is that he's discovering? Is it a proton? Is it a neutron? Or is it an electron? An electron, right? Would an electron be attracted to a positive charge? Mm-hmm. Would it be deflected by a negative charge? Yep. So he's like, oh, wow, this thing gets deflected by a negative charge. It gets attracted by a positive charge. Let's call it an electron. So they found out that on an atom, there are these particles, these negatively charged particles, and they called them electrons. Okay? But that's all they knew. They just knew that these atoms had these negatively charged particles on them. Okay? So their idea of the composition of an atom is now starting to be generated as this electrically negatively charged thing with all these negative charges around it. Okay? Which is a pretty good start because it does just have a bunch of negative charges around it. That's what an atom does. Okay? Okay, so that was the first kind of start of our understanding of these atomic particles. And then later the proton was discovered in the same kind of fashion, in kind of a similar way. And they discovered that same charge but opposite in sign. The proton has the same charge as an electron, but it has an opposite sign to it. And it's a lot heavier. Okay, the proton has a lot more mass than does the electron. Neutrons were postulated in the 1920s, and then later discovered in kind of the 1932, and to have about the same mass as a proton, which we've seen that to be, okay, and a zero charge. So we're starting to get these ideas. Now this is the famous gold foil experiment that really helped us understand how the atom is built. Because before this, we just had this idea that there was this electrons and protons and neutrons, and they're just all floating around in this space of an atom and just ubiquitously just going all over the place. Okay, that's what they understand. So Rutherford, he builds this apparatus that has a piece of gold foil as kind of like a shield, and then he has this receptor behind it that will indicate whether these atomic particles have passed through the gold foil or not. And because he's trying to understand the composition of these atoms. Where are the positive charges? Where are the negative charges? Where are the positive or the other charges? So he takes a positively charged particle of an atom, which are alpha particles, which is in fact a helium nucleus. Okay, just the nucleus of a helium atom. We call it an alpha particle. And he takes this alpha particle, just 2 positive proton charges, a mass of 4, because it has 2 neutrons, right? He didn't understand that's what it was, but he knew that there's this positively charged alpha particle, and he shot it at this gold foil. He shoots it at the gold foil. He shoots a ray of alpha particles at the gold foil. And what happened was very surprising to them. They didn't expect it. They had no idea that this was going to happen. But when he did that, okay, he shoots his ray, and it goes, the ray, mostly all of it, passes right through the gold foil and hits the screen, the detecting screen back here. But then what he saw was a pattern of deflection all around it. Okay? So most of it goes straight through, and then some of it gets deflected. And they were just baffled by this because they had no idea that this was going to happen. Because they expected that most of it wouldn't go through and that you would have all kinds of other deflections. Okay? So what is happening? Well, here's the gold foil. These are the atoms on the gold atomic level. And from this experiment, they were able to determine that, okay, this is what's happening. In the very center of your atom, you have a very dense, small region where the positive particles are contained. So I'm shooting positive particles, and I'm mostly hitting empty space. Okay? You see, most of my particles are passing right through between the atoms. They're just passing right through. But whenever those alpha particles would get close to the nucleus of one of the gold atoms, it would get deflected. Positive and positive charges, they would deflect. Or here, I would hit the nucleus and it would get deflected backwards. Okay? And that accounted for that deflection pattern. And now they understand better. Okay, I now have a better understanding of what the atom consists of. It consists of a small, dense region of positive particles. And surrounding it are the negative particles, the electrons, which are mostly in empty space. Okay? They're mostly in empty space. And I can just shoot those particles right through it. So that's why if you're around something radioactive, just in the next room, right, you can still get irradiated because those radioactive particles can just come right through the empty space of the wall that are in the wall. Okay, just like radio waves. I can receive a radio signal in this room because those radio waves can just travel right through the empty spaces of the wall. Okay. All right, so this was an earlier model of the atom. You just have the particles just swimming around in empty in this region. But then Rutherford's model developed the idea of the positive charge in the middle surrounded by the electrical charge, the negative charges around it, okay, which is more true to the models we have today of that. So that atom has that dense, positively charged region, okay, that we now call the nucleus. Okay. So spectroscopy is the process of measuring the absorption of light in a sample of something. Okay. So how well light will be emitted or absorbed in a sample we can measure, and through a spectrophotometer. And basically light is energy. It's energy. That's what it is. And so if you can measure the light emitted or absorbed in a sample, you can measure the energy associated with that sample. And that's what Bohr wanted to do with spectroscopy. He wanted to measure the energy of these electrons that's associated with their positions. So now we know the electrons are around the nucleus, but where are they around the nucleus? That's what Bohr wanted to understand. And he did it through spectroscopy. He used the spectroscopy. So if we look at a wavelength of light, this is a wavelength of light, okay? From one point on one wave to that exact same point on the next wave, that would be the length of the wave. So we call it the wavelength, okay? Here, the top wave has a larger wavelength than the bottom wave. So what does that mean? It means this one has less energy than this one. More energy. This one has more energy. Why? Well, they're all traveling at the same speed. Okay? Light travels at 3.0 times 10 to the 8 meters per second. Does anybody know what that number is?
186,000 meters per second.
Okay. I don't, well, 100, what did you say?
186,000
meters per second? Well, it's 300, let's see.
That's a big number. Oh wait, maybe it's miles per second. It is what I was thinking.
Doing this backwards. It's 3, 6, 7. Nope. There. Meters per second. Okay? But this has a name. It's the speed of what? Light. That's how fast light travels. Okay? That's how fast it travels. This wavelength travels at the speed of light. Or, I'm sorry, this wave. This wave travels at the speed of light. They both travel at the same speed. But which one penetrates more? This one penetrates more. So if I'm looking at this point right here, and I'm measuring per second how many wavelengths travel and pass that point, which one will have more wavelengths pass? The bottom one, because it has a smaller wavelength, but it's traveling at the exact same speed, right? So that is why there is more energy associated with this one than this one. The smaller your wavelength, the higher your energy. Okay? The longer your wavelength, the lower the energy. So things that have low energy are not very dangerous, but things that have, things that have low or large wavelengths are not very dangerous, but things that have small wavelengths become harmful to us and can damage us. Okay, so that's radioactive energy. A lot of times has these small wavelengths that are damaging to us, and they will affect our DNA and things. Okay, so here is the electromagnetic spectrum of light. You can see over here radio waves. Radio waves are very large. They can be as close as or as big as a football field in their wavelength. They're ginormous. Okay? So we don't care that we're broadcasting radio waves all over the place. Right? We don't care because they're not going to do anything to us. The wavelength is so ginormous, the energy is so low, it's not a big deal. Okay? So we move past the radio into FM. Here's our cellular phones. Okay? And we get into the microwave region. Now the wavelengths are getting a little smaller, but they're still pretty big. They're getting smaller though. We're still not worried about them. Infrared, we're not too worried about. Okay? But then, here's the light spectrum. This is the visible light spectrum. Red light, yellow, green, blue. So blue light has the shortest wavelength of this light spectrum that we can see. We can see blue light. But once we get past it into ultraviolet, we can't see it. Now, the wavelengths are becoming more dangerous. Okay? You can use ultraviolet radiation to kill bacteria and to sterilize things. They do it all the time. If they're going to package something, they'll use ultraviolet radiation to sterilize it. Because now those wavelengths are becoming small enough that they're becoming dangerous. And they could even become somewhat dangerous to us. So if you're looking at something that emits an ultraviolet signal, it could damage your eyes. Okay? And then we're keep moving into the X-ray region. Now we're even smaller. Into the gamma ray. Very bad. Okay? Gamma radiation is some of the radiation that excuse me, that is released from radioactive samples. Not all radioactivity is gamma radiation, but it's the most damaging type, okay, of radiation that is released. So if they drop a nuclear bomb, it releases a lot of gamma radiation. Okay,
But it's slow to kill, though. And it takes 10, 20 years to...
it depends on the exposure.
You are from it, right.
Yeah, if you're right next to it, you're dead. But if you're miles away from it, that radiation is going to be coming and is going to be altering your DNA structure and causing cancer and doing all kinds of horrible stuff to you, depending on the amount of exposure that you get, right? So if you ever work with radiation, you have to protect yourself. If you go in for an X-ray at the dentist, they give you a big lead coat thing to put on you because they don't want to harm your reproductive organs, because that's where most of the damage would occur. Okay, our old cells, they can kind of die off, replenish themselves, but your reproductive organs are constantly being replenished, and they're most susceptible to that. Okay, so that's this is the bad stuff. Okay, this stuff can harm us if in high enough doses, but we're constantly getting radiation, even from the sun. We're constantly getting irradiated. And our bodies can take a certain amount of it. And they've kind of determined certain levels that are more dangerous than others to human individuals. Okay? All right. So Bohr was using this electromagnetic spectrum to understand the positions of the electrons. because their position is associated with a certain amount of energy. So what he would do is he would excite an electron by shooting energy at it. He would excite that electron, and it would jump up to a higher energy level. And it couldn't maintain that high energy level, so it would relax by releasing that energy. And as it would release that energy and relax back to where it originated from, he could then identify its original position, because the amount of energy that it released was the exact amount of energy that determined its original position. And he would measure the energy that was released because he understood this electromagnetic spectrum, and the amount of energy that was coming through would tell him the position of that electron. Okay? And so then he was able to identify for different elements the positions of the electrons around those elements. And our periodic table, okay, so kind of like this. So here's its original position. I'm sorry. So you excite it to one energy level. It relaxes, and as it relaxes, it releases that energy, and you can absorb it, and you can identify its position after that relaxation. Okay, so it goes to its excited state, and then it relaxes. Okay, and he started to develop these ideas that, okay, atoms have positions around the nucleus in what he calls orbitals. So certain electrons orbit at this energy level, and certain ones orbit at a higher energy level, and other ones orbit at an even higher energy level. And that's our periodic table actually reflects that. The energy level of electrons is identified right here. Hydrogen has 1 electron. You see this number on the side, 1, 2, 3, 4, 5, 6, 7? Hydrogen's electron is in the very first energy level. Helium's has 2 electrons. Both of them are in the very first energy level. Lithium has 3. 2 of lithium's electrons are in the first energy level, and its third electron is in the second energy level. Oxygen has 8 electrons. 2 of them are in the first energy level. 6 of them are in its second energy level. Magnesium has 12 electrons. 2 of them are in the first energy level. 8 of them are in the second energy level. And 2 of them are in the third energy level. Okay, so we're starting to develop these ideas of where the electrons are. So something for magnesium, for example, here's the magnesium nucleus. The first energy level, 2 electrons. The second energy level, 1, 2, 3, 4, 5, 6, 7, 8 electrons. And the third energy level, 1, 2 electrons. Okay, that's magnesium. That's where the electrons are found. We say that these are the principal energy levels. 1, 2, 3, 4, 5, 6, 7 are the principal energy levels of these atoms. So you can have up to 7 energy levels on an atom. So francium number 87 has 7 electron shells, we call them. These electron orbital shells, these energy levels around it. It's a very big atom because of that. Because it has those 7 layers around it. Okay? Now within those energy levels, those principal energy levels, there are also found sub-energy levels of the electrons. The sub-energy levels are also identified on the periodic table, kind of as groups. Okay? Sorry. See this column? These two columns? They're a group, right? You can kind of see that. That's one of the sub-energy levels. You see this middle portion right here? Elements in that portion are in a different sub-energy level. See this portion? That's an even different sub-energy level. And then lastly, this portion. Okay? So the periodic table is developed and designed to have the elements in their principal energy level and their sub-energy level. Okay? And that is reflected by Bohr's work here. He's the one that helped us understand the sub-energy levels and the principal energy levels. And now we can develop a nice periodic table that reflects all of that. Okay? Okay. Okay, before we get to that. So let's just look at kind of an example of this Bohr atom model. So let's just start drawing an atom with a generic nucleus. Okay, so here I have the nucleus. It could be the nucleus of anything. Okay, and it will be. So I start with hydrogen. Hydrogen has one electron. Now, electrons on the outside of an element we always call the valence electrons. So hydrogen has one valence electron. When I get to helium, it gains another one. And you notice how I pair them? Electrons pair. That's what they do. They pair because they don't like to be alone. And in fact, a lot of the chemistry that occurs is because you have unpaired electrons. If you have unpaired electrons, they want to pair, and so they're going to find those other electrons from something else. And then they're going to pair and form new compounds and things. Okay? So hydrogen with only one electron is reactive. Helium, 2 electrons, not reactive. It's paired, it's happy. Helium is a non-reactive element. It's inert because it has what it wants. It's good to go. Okay? That's the first energy level. We build the second energy level. We have the 2 that are there, and then we go to lithium has one right here. Unpaired electron. Okay? And then it has magnesium. Now, magnesium is not inert. And that is because this first energy level can only hold 2 electrons. And you pair those 2 and it's done. But this second one is bigger. It holds more than 2 electrons. So it's not done. It has all this empty space that it wants to fill with electrons. So sodium can react with things. Magnesium's reactive. Lithium and beryllium are reactive. And then you get to boron. Okay? Now you notice when I went from beryllium to boron, I'm now in a different group. I'm in this group now. So this first group, they pair with themselves, those 2. But when I jump over here, these guys will pair with themselves. Okay? So, but first they spread out into 3 groups. 1, 2, 3. Boron, carbon, nitrogen. And then they'll come back and pair with themselves. Okay? Oxygen, fluorine, neon. I have just filled up this energy level. How many valence electrons does neon have? 8. Has 8 valence electrons. That's the magic number. And we'll talk about it next time. See you guys.